Okay, so hey everybody, this is Mr. Bells, and this is a little assignment on section 4-8. There's quite a few trig application problems in this, so I'm going to try and give you at least a little bit of stuff on these. Again, they're not going to match perfectly, but hopefully this will at least give you an understanding of some of the stuff that we're going to do. So the first thing we need to be able to do is we need to be able to look at a problem like this one right here. So again, on trig applications and extensions. So this is a basic right triangle, and we have to have that understanding for it. So if I'm trying to figure out what x is, then I need to know that that side, again, is the opposite side, and this side's the adjacent side. And then opposite and adjacent means cosine. So I'm going to do cosine of 56 degrees equals opposite x over adjacent 60. And unlike the other ones where I've had to flip-flop because the x's were down in the denominator, this time the x is upstairs. So I simply need to multiply both sides by 60, and that should get me what my x is. So I go to my calculator. I'll go ahead and turn that on right now. Turn that on. I'm going to clear out that graph and go to home screen. There we go. And I want to do 60 times the cosine of 56. So I'm going to do 60 times the cosine of 56. And I hit enter, and I get 51.19. 51.19. And I look over here at this, and I see that this angle is bigger than 45 degrees. So that means that that side cannot possibly be 51.19. And I think to myself, well, that's DIMS. That doesn't make any sense. So what must I have done? And that's when I remind myself, oh yeah, every time I do one of these problems, I need to check the mode. And you can see the mode on my calculator was in radians, and I was doing this in degrees. So I'm going to change it to degrees. You can see that right there. Go ahead and quit again. I'm going to do 60 cosine 56. Then you can see that that is 33.55. And then I'm like, wait, that doesn't make any sense either. So, and again, I did this on purpose. This is opposite and this is adjacent. And I'm like, oh, no wonder I couldn't use cosine. Cosine, whether it's in degrees or radians, doesn't make any sense for this one, because I know that this side has to be longer than 60 feet. And then I realized, oh, I needed to use tangent. Okay, so a couple different things that you can mess up when you're going along with these, and those are the things that I want you to be able to get. Remember, been preaching this since day one. Does it make sense? So let's try it with this one. 60 tangent of 56 and hit clear. I get 60 tan 56, hit enter, and I get 88.95, and that looks like a winner to me. If that's 60, that should be longer than that, 88.95 feet. And again, I don't really care about how much are you rounding in this thing right here. You can go with whatever you want on that. That kind of makes sense. I'd probably say to, as you're doing the problems, if they have multi-steps, like some of these are going to have later, don't round it all till the end. But once you get to the end, hundredths is usually fine, sometimes tenths. Okay, so let's try this next problem. So this next problem shows you have multiple triangles in here. And what we're trying to find out is this distance right here. Well, it looks like, based on what you see here, that I've got a couple different things going on. I have this triangle, the smaller one right down in here. And I can probably use this triangle to find out this distance here. And if I use the big triangle to find out the total distance, looks like I just have to subtract those two things to get how long x is. Because I don't have anything for, I don't have a formula for that weird shape. Okay, so let's try with this small triangle first and try and find out what y is, which is this distance right here. So I know y is the opposite side, 80 is the hypotenuse, so opposite and hypotenuse, and this time we're going to take our time with this. So that is, opposite and hypotenuse, so I need sine of 16 degrees equals opposite y over hypotenuse 80. I'm going to take my handy dandy calculator out here. I know that I have to multiply by 80, so I'm going to do 80 times the sine of 16 degrees, and I get 22.05. So y equals 22.05. Now I'm going to do the same thing with this whole length. We're going to call this whole length, let's call it z. And I know that z is the opposite, and this time I have the adjacent 200 feet right here. So opposite and adjacent, that's tangent, TOA. So tan of 20 degrees is equal to, in this case, I probably should have switched this up. Maybe I didn't copy this out of the thing right. Let's go ahead again. If this is further away, the angle is actually going to be smaller. So let's make this a 10. So if you already copied that down, make that a 10 degrees. In fact, let's just scribble that sucker out and throw in a 10 degrees in there. So tangent of 10 degrees is equal to z over 200. Okay, so tangent 10 z over 200. So I'm going to do 200 times tangent 10, 200 times tangent of 10, and I get 35.265, 35.265, and I simply subtract the last answer that I had in there, the 22.05, and you can see on my calculator I just went up and copied it from up above. Remember, you can store it if you like to on that and do it that way. So 13.21, and that's, I'd probably go ahead and do it like that. So 13.21 in this case. Feet is how long that little distance is right up there. Okay, so that one has a little bit more complicated stuff to it. So sometimes you're going to have to do part of one thing to be able to use it with part of another thing to get to your final answer. Okay, so here we go. Let's go and talk about something a little bit more detailed now. So I've got a ship, it's traveling at 18 knots on a bearing of 115 degrees for 4.5 hours. You're like, whoa, well, what does that mean? Well, first, bearings. I'm going to do that right over here. So a bearing always starts from due north and rotates clockwise. So when this says it's a bearing of 115 degrees, I need to have this. 90 degrees would take up this first part. And then 115 is 25 degrees more than that. So that means that I've got to have an extra 25 degrees into this quadrant. Is that okay? And we know that this is going on, traveling at 18 knots. That's a term for its speed in terms of on the water, for 4.5 hours. So I'm going to do 18 times 4.5, 18 times 4.5. And you can see that it's going to travel a length of 81 in this direction. Okay, and then from that point right there, it then travels at a bearing of 205 degrees. So that means I got to put my little crosshairs right in here and go 205 degrees, which takes me right to here, which tells me that that angle right in there, because that's 180 degrees, 205 is 25 more than that. It takes me to a 25 degree angle right down there, and I now know that this is going to go for, what does it say, 3 hours? So 3 hours, the speed's going to stay the same, so it's still 18 knots. So 3 times 18, 54, so this one's going to go at 54. And I'll make it kind of about the right distance. That one's 81, that needs to be a little bit longer. 54 is a little bit shorter. And you can see when you work out the angles here, if this is 25 and this is 65, and if this is 65 and this one right here leaving with 5, that's a total of 90, which means my inner thing must be 90 also, and I've got myself a right triangle. So it says find the distance and bearing from where it started to its final location. Well, the distance would be this distance right here, x. And since we have a right triangle, and I have the two legs, I can go ahead and use Mr. Pythagoras. And Pythagorean theorem says that if I square 81, so 81 squared plus 54 squared, enter, and raise it to the 0.5, which is a square root. I get 97.35, and that's rounded, but that's okay. So distance equals 97.35 from where it started. Now I need to know what the actual bearing is. Well, the bearing is this from due north right here. So I've got 90 plus 25 plus whatever that angle theta is right there. Well, how do I figure out an angle? Well, I simply can use, since this is a right triangle, I can use the 81 and the 54. And the 81 and the 54, this would be my opposite. This would be my adjacent. And then I can go tangent. So tangent of my unknown angle is equal to 54 over 81. And I know that I got to use tan inverse of tan to kill that off. And if I do it to one side, I have to do it to the other side. And just like this. So on my handy dandy calculator, I'm going to go second tan inverse of 54 over 81. And I see that that's 33.69 degrees. So 33.69 degrees. That's what this is. So I add 90 plus 25 plus 33.69. I'm going to add those all together. So plus 90 plus 25, I get a bearing of 148.69 degrees. So bearing of 148.69 degrees. So that's what that problem looks like. Again, some of these problems are going to be a little bit more detailed than other ones. Take your time with it. Draw stuff out just like I do. Got some scrap paper here, write some stuff out on it to process it all out. It was a little high from my dog. Bella's in the other room. Okay, so now we're going to go into some different kind of problems. So we talked about in our graphs what a dampening was, what an oscillation was. I think in some of the homework problems we talked about guitar strings. So we're going to talk about a spring right now. So I got this spring that is locked all the way up the top, and I go ahead and stretch it out and snap it and let it bounce back and forth. And it'll go from 0 right here. It'll go up 12 centimeters, and it'll go down 12 centimeters, and it'll keep bouncing along in that little range from the baseline 0. And it says it completes a cycle in 0.25 seconds. So that means from the middle, it'll go all the way down, all the way up and back to the middle again in a quarter of a second. And what it's asking is, can I find a model that works for displacement after t seconds? So what exactly does a model mean? A model simply means an equation that matches this function. So what we're going to do is we're going to say, hey, since it's, I'm going to pull it all the way down to the bottom and let it go, and it's going to go back and forth from this middle. Since I started the bottom, I'm going to go ahead and use a cosine model. And as we go through more and more of these problems, sometimes we'll use cosine, sometimes we'll use sines. Remember, they're both sinusoidal functions. It's just sometimes one works better than others for the way that the problem is set up. So now I got this. So I got y equals, I know I got a cosine. And so what goes out here in front? Well, that's the amplitude of how far up or down it goes. Since it's a baseline of 0, it goes up and down 12. We simply put in 12 in front of that cosine model. And then it's 2 pi over how long it takes to complete one cycle. And that's 0.25. And then t represents seconds. So if I want to simplify this, it would look like this. Y equals 12 cosine 8 pi t. And that whole thing would go in parentheses just like that. And if you took that and you put it into your graphic calculator and you set up your window for it, in fact, let's go ahead and do that. We got a few seconds right now. So I'm going to go here. I'm going to go y equals 12 cosine, and then we're going to do 8 pi. We have to use x for seconds. And then on my window, I'm going to go x min from 0 to, I'm just going to do 1. I'll let you see it that way first. And then from negative 15 to 15. Okay? And again, this was in radians. Again, radians because I used pi. I didn't use degrees. I would have used 360 if we were doing this in degrees. So radians. Got to change it to radians. And then go ahead and hit graph. And you can see that the spring starts right up at the top. We release it and goes down 12 below the baseline, and then up 12, and then down 12 again for each one of those things. And you're like, wow, why is there so many of these things? Well, remember, I did this for, in the window, I did it for 1 second. And we said that the cycle takes 0.25 seconds. So if I do this to 0.25, change the x to 0.25 and hit graph, you should see that it should complete one complete cycle in 1/4 of a second. Now, of course, if I was to not really know what the heck was going on, and I did this x max thinking, oh, let's do it at 360, right? Like, I don't know what this is. I changed my x res to 4 to make it go faster, and then I hit graph, and yeah, it doesn't even know what to do with that. So be very careful when you're graphing these things to make sure that you have stuff that makes sense. It's going to try and draw a model that's close to it. But remember, if I went to 360, that actually means there's over 1,000 of these bounces up and down in this window. It just doesn't know how to connect them in that frame. Okay, so let's get rid of that. But that's a spring. That's an oscillation model for a spring. And we're going to go to our last one from this unit of stuff. So here we go. It says a Ferris wheel. Boy, wish we could kind of go there right now, huh? Amusement park. Ferris wheels are a little bit easier to model than some of the roller coasters because roller coasters have so many other things to them. We can model parts of roller coasters, but not necessarily all of them. Ferris wheels are a little bit easier. So a Ferris wheel with a circumference of 200 feet has a high point of 70 feet. It completes 1 revolution in 40 seconds. So I got all of this information right here. And my first question says, please write a model that shows height based on time. Ooh, a model of a Ferris wheel based on that stuff. Well, the first thing that you'd have to know is that a Ferris wheel goes around and around and around. And if it's completing a cycle like this, then we know that that's a sinusoidal model. And if it's a sinusoidal, that means I can model it with either cosine or sine. So what I look for, just like when we were doing those tide problems, not laundry detergent, but tide of at the beach, of water going in and out, we want to know, does it start in the middle, or does it start at a high point or a low point? And it says, if Sally starts at the top, top means cosine. So let's try and see if we can model it with a cosine. So we know y equals a cosine b x minus c plus d. All of these things help us understand what happens with this. So this a, it tells us how far up or down it goes. The b tells us how often it goes around. The c tells us, in terms of the Ferris wheel, it's like, how do I shift it around my Ferris wheel, forward or backwards? And D means, how do I get my center point right up into there? Okay, so let's first go, what are some of the things on this that will help us? So I'm going to deal with the A first. Well, the A is how far up or down it goes. Well, if I look at this Ferris wheel over here, doesn't that make sense that that's just the radius? Sweet. So if I know my circumference is 200 feet, if I simply divide that by 2 pi, make sure I put that in parentheses, that should tell me my radius. So I'm going to come over here to my handy dandy calculator, and I'm going to do quit clear 200 divided by parentheses 2 pi. Okay, I get 31.83098862. I'm like, that's a lot of stuff to remember. What should I do? Say it with me. 1, 2, 3, go. Awesome. Hopefully you said I should store that in R. So store it in R, alpha R, enter. Now I know that that's my radius and I can use that. That's pretty good. So now I know I'm going to actually start using stuff. So the height of the person on the Ferris wheel is equal to, and I'm just going to round the stuff when I put them in here, 31.83. Again, I'm going to use cosine because it said that she started at the top. If she wanted to start at the bottom, I would use negative cosine. And you'll see that in just a little bit when I start doing some models of here. And then b, well, that's 2 pi over, how long did it say it took to go all the way around? Right up there, 40 seconds. So that's 2 pi over 40. And x. And you're like, well, why isn't there a C? Why isn't there a C? Well, I told you that she started at the top. And if we're going to use a model that starts Sally at the top, then we don't need to shift her anyplace. If we were using sine, we might have had to shift her back 10 seconds or forward 30 seconds to get her to be at the top when we're doing this. Okay? And then plus D. Well, it says someplace up here somewhere. I'm hoping that this makes sense. That Ferris wheel has to be someplace off the ground. If not, when the people are coming down around the Ferris wheel, we're going to shave their legs off, right? That would be very good. So it's got to be lifted off the ground a little bit. So we know that it's a height of 70, right there. It says 70 feet. So if I do 70, which is the high point right here, minus the radius, it'll tell me how far off the bottom of the ground this thing is. Does that make sense? Good deal. Hopefully that works out for you. So my D is actually going to be 70 minus the radius. Okay, so I'm back to here. And I'm going to do 70 minus alpha R. Hit enter. And I get 38.17. 38.17. And I know that that will be how far I need to shift it up to get me right into the center of my Ferris wheel. Okay, so let's go ahead and model this because that's what I need. This should be my model right there. Let's go ahead and scratch out D and put 38.17. So that's A. That's A's answer right there. That is a beautiful answer for that. And now to answer questions about it, I could ask lots of questions. I need this to get this. So we're hoping right now that this model, when I graph this, actually looks like what it's supposed to. So here we go. Y equals. Nice thing about this is I can still use R. I'm going to do cosine. I'm going to do 2 pi divided by 40. And then parentheses, open parentheses. Don't close them or else it'll just cosine that and it won't treat the x with your cosine. Double close. Again, no shifted needed. Remember, no shift because we're starting right on the top. And that's because we're modeling it with cosine. And then plus that 38.17. Or if I want to be exact, I'm going to do 70 minus the radius. Okay? That's it. That's my beautiful equation. So I go to my window and I go, okay, what does my window need to look like? First off, double check again. Use 2 pi, right? So we're going to use mode of radians. Still in radians. We're good. Could have used 360. It does not matter. But if I use 360 here, then I've got to use it in degree mode. Okay, so back to my window. So x represents time in seconds. So we said it takes 40 seconds to go all the way around. So let's do it for 40 seconds and see if I get one full revolution. And then y min and y max. I'm going to go, I usually like to go below the ground just so I can see it. And I'm going to do 80 for the height. Okay, ready, set, and cross your fingers. I'm going to change the res back to 1 because I do want it to be a nice, pretty graph. And it looks like that is showing the height of the person as they go around the Ferris wheel. I'm feeling pretty good about this. Let's hope. So I do a couple checks on here. I'm going to do on this one y equals 70. And on this one, I'm going to do 70 minus 2 of the radiuses. That should be the bottom. And when I hit graph, they should be at the top. At the bottom, I'm like, yes. Makes sense. The other thing that I should be checking right now is the minimum of this blue. So second trace, I'm gonna do a minimum, and you're like, why do you need to do a minimum? Well, let's see if this makes sense. Enter, and guess. 20 seconds. Well, if it takes 40 seconds to go all the way around, it should hit the bottom point at 20 seconds. Sweet. So it says if Sally starts at the top, how high is she 53.5 seconds later? So the first thing I'm going to ask is this a perfect model? And you're going to say yes. So if I want to know 53.5 seconds later, doesn't it make sense that I can just go to my table setup? I don't even have to see this on my window. 53.5 seconds later, I'll go up by 1 second, and you can see that her height would be 21.537 feet off the ground. We can use this to model any of the things. If I wanted to know when does she hit a certain height, like maybe when does she hit 50 feet? Let's go down to here, and I'm going to clear this off because I don't really need that. That was just to help you understand the problem. Let's go ahead and say, well, during her first revolution, when does she hit a height of 50 feet? Well, again, this is the graph. I might switch this to simultaneous mode so that those can both go at the same time, but you can see she hits a height of 50 feet 2 different times. Do second trace intersection, enter, and find that point and that point. We could do this all algebraically, but that might be brutal in terms of plug in 50 feet in here, divide them by 31.83, doing well, actually, before I divide by 31.83, I'd have to subtract this number, then divide by 31.83, then take the cosine inverse of it, and then divide by 2 pi, then multiply by 40, and that would get me to my x. But doing all that would get me the exact same thing that I did before. So this is a nice big model of the problem, and hopefully this was really helpful. The last few things I'm going to do, because that answers that question, is just kind of show you a couple stuff. So if I simply did this second insert and I made this a negative in front, watch what happens. I simply have modeled Sally perfectly on the same exact roller coaster, except with her getting on at the bottom, or at least starting the count time from when she passes the bottom, because that's using a negative. So if I go here and I get rid of that negative and I say, hey, let's start her in the middle of it, and I hit the graph, you can see that since I use a positive sign, it starts her right at the halfway point, or even with the metal spoke of the Ferris wheel. And if it's positive sign, it's when she goes up. And if I go back here again and I insert a negative and I hit graph, that simply means that she starts going down first. So depending on if she's rotating clockwise or counterclockwise or whatever it is that you want to do with this, we can make it positive cosines or negative cosines or positive signs or negative signs. Awesome. Okay. The only other thing that you could do if you wanted to is this. Let's go ahead and delete that and move back to the cosine. And remember, this started right at the top, correct? So I'm going to go right here and I'm going to do a little tweaking, and second insert, I'm going to do minus 10 right in there in that set of parentheses. And then I'm going to go ahead and hit graph. And now you can see if I did a minus 10, that actually moved her 10 seconds difference in terms of the graph. So instead of the cosine being here, right here at the top, we've moved it 10 seconds forward. Okay, so if you wanted to do that, you can shift the person forward that way, where you could always use cosine and shift 10, 20, 30, or 40 seconds to get her at any one of the other spots. Hope this has been helpful to you. Again, hope the videos have been helpful to you. Stay with it. I know this is not always easy, especially without having me there in front of you all the time. But I'm doing what we can do to get us through some of this stuff. So take care. Again, hi to all the moms and dads that are out there listening in the background. Thanks.